welcome Ben Landon, who will give the final talk of the day.
Thank you very much. Today I'll talk about work in preparation with Christian and Phil at Cornell University, who I believe are both in the audience. So, if I say anything incorrect, hopefully they can correct me. So we're going to study a system of interacting diffusions, and the motivation for the system we study comes from integrable probability. So I'd like to first introduce one model from there. So O'Connell and Yor introduced the following stationary version of a directed polymer in 1+1 dimensions. So here there are, these Brownian increments right here. There's a parameter theta, which is strictly positive. Importantly, the domain of integration is just from -infinity all the way up to t. There's the convention that Sn is equal to t, and all the BIs are two-sided Brownian motions. So maybe another more commonly studied version has S naught is equal to 0, and the B naught and theta aren't there as well. So this polymer and its variance are important models in integrable probability. So I'll just say a few results that are most relevant to the current talk. The first is the work of Landon and Valco, who proved that the variance of the free energy, so the log partition function of this model, is bounded above and below by a constant times n to the 2/3 for n and t growing in characteristic directions. And Borodin, Corwin, and Ferrari proved the Tracy-Whittam-2 fluctuations for various polymer models, proving that they lie in the KPZ universality class. So just a slightly different perspective on this model is the following, which will motivate the model we introduce, which is to introduce the following increments. So first, u1 of t is equal to log z1 of t plus b naught minus theta t. And then the increments between the partition functions at different values of n will be denoted by uj of t for j bigger than 1. So as a consequence of the Burke property for this model, for every fixed t, this collection of ui of t are IID, and their law is proportional, the density of their law is proportional to this e to the minus u of x minus theta x, where u of x is this negative exponential function. In particular, you can rewrite this free energy as a sum of the uj of t's and this Brownian motion. In particular, what we've done is that this is now a sum of a bunch of IID random variables, and then there is a Brownian motion which is correlated in some funny way with that independent sum. Now, if you apply Ito's formula and take the d, the stochastic differential of these quantities, then you find this kind of a system where, so it's a system of, so this is a system of diffusions. du1 has this quantity, this has this equation right here. And then it's a triangular array in that, the equation for uj just depends on uj minus 1. And then also some of the Brownian terms, right, will get coupled to each other as well. So with this system over here, this motivates the definition of the model that we'd like to study. So by analogy with the stationary version of this polymer, we'll introduce the following diffusions. So we'll take a smooth potential, and I'll say what the conditions on it are in a little bit. And we'll define the following system of diffusions. So here's vi of t from I equals 1 to n for positive times t, by basically just taking the equations that we had on the previous slide and replacing that exponential potential with some general smooth potential. So again, the system is triangular. The equation for dvj just depends on vj minus 1, etc. And for the initial data, we'll take it IID with density proportional to e to the minus v minus theta x, which is the invariant measure for this system. What I should have said is that I called the polymer I introduced at the start a stationary version, and the reason is that the things have some stationary distribution. So then the observable we're going to study is this height function in quotation marks here, which is just the exact same thing we had in the stationary version of the polymer, where we take this sum of IID random variables and subtract from it the Brownian motion, which is driving the first coordinate. So the theorem in our forthcoming work is as follows. So if n and t are growing in characteristic directions, which I'll define in a moment, and if the potential satisfies some conditions, which I'll also say on the next slide, then we have an estimate for the variance that is bounded above by a constant times n to the 2/3. So the conditions on the potential are basically that it's positive and that the first three derivatives alternate sign and they're comparable to each other in this sense for each x. We don't need all of these inequalities, but I just write it like this to not have a giant list. A fairly general class of examples is furnished by just taking some positive finite measure that's supported away from 0 and has bounded support, and just by integrating, this sort of what we call the O'Connell-Yor exponential function against that measure. You can also take this potential v and perturb it by like elements of compactly supported smooth functions, as long as you don't make the perturbation too big, depending on which phi you take and the measure mu. The main point here is that in general, we don't expect these models to be integrable in any way, and our techniques are analytic. So what the characteristic directions are is that, so we take what is basically the generating function of v of x, but just the signs backward, but never mind that. So we take this psi of theta, and then we take the n and t have to satisfy that they're related to each other by this inequality. Note that the second derivative of psi with respect to theta is positive, as that's just, of course, the variance of some random variable. One thing to also note is that there's an easy lower bound, which just says that the variance of that quantity is bounded below by the absolute value of that. Of course, this thing could be 0. And in particular, we don't have a general matching lower bound for our upper bound at this point. So let me just spend a slide going through just mentioning a few elements of the proof. So the first is a certain representation for the variance, which is related to a expression for the variance in the paper of Landon and Valco that they had for the stationary version of their polymer. So the first equality just comes from, you have the sum, h is just a sum of all these ui's and the Brownian motion. So if you write its variance, you just get the variance of both terms and some cross term, and then the cross term we just sub back in for h. So the variance of the ui's is just giving us this psi of theta because the distribution of ui is invariant in t. That's just coming from the Brownian motion. Now this term right here, we're going to use a type of Gaussian integration by parts where this ends up getting related to a certain derivative of the height function with respect to the parameter. I'm being a little bit vague about what this derivative is, but I'll talk about it a little bit more in a moment. Now, the main idea is to use some convexity. So what you see is that this term right here is going to be n to the 2/3 because that's the assumption of the characteristic directions. So we have to estimate this quantity over here. So we'll look at its square and we'll apply a Schwartz like this. Now, if this is a convex function, then you can bound it by a difference quotient from above. So where you just look at the system for slightly different values of the parameter. Then what you do is, of course, you add and subtract back the expectation, which I've denoted by u sub theta and u sub lambda. And then you'll also get the variance at the two different values of the parameter. So you'll get the difference as well. Then you need some equilibrium calculations, basically, which tell you that the derivative of the variance with respect to theta is order n. And then the derivative with respect to theta of the expectation is order n to the 2/3, where this also uses the fact that you're in a characteristic direction. After this, you optimize over what you get on the right-hand side, which turns out to choosing lambda and theta like this. And you end up with a bound, which is that the variance is bounded by, because here we had a square, so there's going to be like, this is less than the square root over here, so there's square roots everywhere. You'll end up with, variance is less than n to the 2/3 plus n to the 1/3 times it's the square root. So you get this inequality at the end. So the main problem here is that the derivative coming from the integration by parts is a derivative with respect to the theta and the system of stochastic differential equations, but not with respect to the initial data. So in order to make this kind of program work, of course, first you have to check convexity. And you also need to choose couplings correctly to add back the derivative with respect to the initial data, because that's not included up here. And you also have to check that adding back this derivative doesn't screw up the convexity too much as well. Okay, that's everything I wanted to say. So thank you for your attention. And I hope everyone has a safe and relaxing Thanksgiving.
All right, thank you, Ben. We have time for questions if people have them. Unmute yourself. Well, let me ask. So I know I had asked you offline this question or some variant of this a few days ago, but so do you have a sense as to how this argument relates to the stuff that Sepalainen and Balash were doing for microscopic versions of this, these zero range processes? Or these
I mean, this one I'm not too sure about. Maybe if Phil's still here, he might be able to shed some more light on that.
I remember that they kind of varied the densities and.
Yeah. I mean, so I think that's somewhat similar, but yeah, I mean, here, like, I mean, for us, like, the big thing is really just that the couplings have to be chosen correctly, because if they end up being in, but what I mean is that when you couple all the different values of the parameters together, if you do it in an incorrect way, these things might not be convex, which kind of destroys what this argument is.
So the coupling is the coupling of the two different solutions together for different.
Yeah, so because really there's two parameters.
So is it not like a basic coupling, or it's a
so I mean the one, so there's one for the initial data and one for the value of theta in the SDE. How we've written it right now is that the way that you couple the initial data together is through basically allowing the system to evolve for a very long time with respect to the eta, and then running it with the other theta, and then that shorter time interval after is where you're actually sort of setting up the height function. But the original amount of time you let the system evolve is to reach equilibrium. So you're using some sort of ergodic coupling.
I see. Other questions? Okay, so let me stop the recording.